But first up, let's welcome Josh to the stage.
Good everyone. As Silvio mentioned, I'm Josh. I'm one of those people whose favourite programming language is solder, and so I thought I would talk about hardware design because I spend a lot of time doing that. In particular, I'm going to talk about how I built this little keyboard, which I'll pass around. So there are two parts getting passed around. One's the finished keyboard, the other one is just a circuit board, which I don't have photos of up there. But basically, I'm going to take you through everything from coming up with an idea through designing a schematic, laying out the circuit board, making a case for it, getting firmware on there, and finally I'll show you how to profit off all of the above. So with that said, why did I design that weird keyboard? I spent a lot of time in KiCad, as you'll see quite soon, and there are a lot of key shortcuts and combinations which are really awkward to press. And there's a few other ones which I just really like some knobs just to turn left and right to make numbers bigger and smaller. And so I thought, well, I'll make a keyboard where I can program every single key to be exactly what I want it to be. I thought I'd add some rotary encoders because there's two individual settings in KiCad specifically that I really wanted them for. LEDs, because why not? And although there are some professional things that meet the top three requirements, or the top two primarily, they're in the thousands of dollars, and I don't have that money because I don't do it professionally, so I wanted it to be cheap. And so I thought I'd build my own. So with that said, the rough idea that I had for it was that we would have some key switches. It had to be mechanical, of course. Have two rotary encoders that would go into a microcontroller. The microcontroller would do all of the logic going, always press this key, we need to send this thing off to the computer. Obviously need a USB connector for that, and once again, our ever important LEDs. So I did some Googling around, and what I found is about on the internet, there are a few great sites. That bottom kind of block diagram is what it would look like if we bought off-the-shelf components. So SparkFun have a few little breakout boards that we can put key switches in. They also document how to assemble them onto a circuit board. You can pick up some rotary encoders, and there's some guides online that show you how to wire that all up as required. You've got an Arduino there. This is a slightly different one to the normal Arduinos we use. This one, instead of using a 18 mega 328p, it uses a 32U4. What do those weird numbers mean? The main difference with this is that it will talk directly over USB to the computer, whereas a 328p can't go directly to the computer. It's going to run through a serial translator first. The reason why that's really important is because we just can't send normal serial data like you would when you pull up the Arduino IDE. We need to send HID commands, which is human interface device, which can be mouses, key presses, all that jazz, and finally our LEDs. But how do we come up with the schematic for all of those parts? I've been doing this a little while. I might be able to make an estimated guess at it. But if you're buying parts from off Adafruit or SparkFun, which they do a great job, they have their breakout boards for basically everything. Online, they will have all the data sheets and the schematics that show them how they made that breakout board. And so you can prototype with their board, steal their schematic, integrate it directly into your product, and you know everything's going to work properly. Depending on other manufacturers, if you're buying, say, like a ST dev board, they will have evaluation boards, there'll be application notes that will show you how you can put that part in application in a circuit, because the manufacturer's job is to sell their parts, and if they make my life easy by explaining exactly how I have to go about doing the design, I'll buy their parts. And finally, the data sheets will have some information. They're the worst place to look, but they do have them in there. So an example of that, oh, that's the wrong thing. Oh, there you go, it's moved. That's a bit different on my screen. So this here is basically a schematic for that Arduino board that was in the middle here. So you can see, even if this doesn't make much sense to you what's going on, you've got a big microcontroller in the middle, which is that black rectangular chip. On the left here, we've got our USB inputs, we've got some oscillators, we've got our inputs and outputs. But the best thing is you don't need to know what any of this means as long as you can duplicate that onto your schematic. And there's a bunch of guides on the website, and I'll give you a quick run through of that today. So with that said, just want to draw up the schematic. I use KiCad or KiCad. Apparently it's actually pronounced KiCad. They should have put an E in there if they wanted it to be KiCad. It consists of a number of tools. We'll primarily be using the top two, Schema and PCB New, which draw up the schematic and do the layout. And yeah, so with that said, what's a schematic? This is from XKCD, so it's not quite what you typically see in a schematic. But what it is an abstract representation of all the components and all the wires that run around your board. The reason why I'm using the word abstract there is because you want to make it so it's easy for you to read and understand. When we get to the layout stage, the pins are all scattered all over the place, the parts are really small, there's no nice labels on the board to tell you where everything is. In your schematic, you can do all of that. And a great schematic, if it's drawn well, is basically documenting itself. You can put notes on there, you'll have all your inputs on the left or your outputs on the right, and it will make sense, hopefully. So with that said, the key steps of going through the schematic, this is more so if you want to go through this later. All this is up on GitHub and there's a slide at the end, so I know some people taking photos, feel free, but it's also all online. I'll run through that as we do the demo. So with that said, when you open up KiCad, whatever, this is the screen that you get here. We'll click on that top little left-hand button up there to open up the Schematic Capture tool. Hopefully this is somewhat readable on the screen. And so you can see here, this is part of the keyboard. I'm going to add a little bit in here for you today, but this will take a little bit too long to draw up. Basically, if we scroll in at the top here, as the label on the schematic quite nicely says, it's a microcontroller. We've got our 32U4 here, which is that black chip that's going to do all the processing. On the left here, we can see we've got a USB connector. In this case here, I run it through an ESD protection because I generate a lot of static and I'd probably kill my parts otherwise. From there, if you look between this and this image, it'll almost look identical. And that's because I either stole it from Adafruit or I stole it from someone else that had the exact same reference design because I want my boards to work first time, and that's the best way of going about it. Otherwise, on this board, up here we've got a bunch of keys in an array. This way we don't need an individual pin for every single key that we want to hit. The ever important LEDs down the bottom here. If you've ever heard of NeoPixels from Adafruit, these are the same part. They just allow you to have one data stream that runs the whole way through. It makes layout nice and easy. But the part that I'm going to demo today is Rotary Encoder. So we've got a encoder on there. You'll notice the keyboard has two encoders, and I thought I'd just quickly show you how to add an encoder, and this same thing would apply regardless of how big your board is. So with that said, kind of the first part is putting down a component. So I should have hit A before we started. You add a component onto the board. KiCad has a really big component library. It doesn't have everything that you need, or sometimes they will have a part and I just don't quite like the way that it looks, so you can make your own. I won't cover that tonight because there's not time, but at the end there'll also be a bunch of resources to people that will take you through step by step on how to design your own boards. This is more of an overview. So now with here, you can see there's almost 15,000 different items that we can pick from. In this case, we want a rotary encoder with a switch. So just type that in and select it. We'll put that down there. We now want a resistor, so I'm going to hit A to add, then we'll hit R, pull up a resistor. Now I've got that down there, I'm going to hit R again to rotate it, and what we'll do, we'll just scroll in a little bit and put that down there. I'll then hit M, and we'll just move these symbols around a little bit. We want to give this resistor a value, so resistors come in a bunch of different values. This one here, we want to be a 10K resistor, so I'm going to hit V, which is going to let us change the value. I'll type in 10K and press enter, and there's a 10K resistor. But you'll notice that these aren't connected at all. So what we now need to do is, I'm just going to actually, move that over a little bit. We're going to hold our cursor over one of the pins of the part. I'm going to hit W, which is going to draw a wire, and I'm just going to go up and click as we go along and draw a wire between those parts. So now we've got pin S2, which is one of the two switches on the encoder. It's going to go to the resistor, and we want this to go down to ground, so we're going to do the same thing, draw a wire, W for a wire, double click down there to finish it, and then we're going to hit A, and going to get a ground symbol. So there's a bunch of different symbols for different power rails, different grounds. You can pull them in as required. On the top right hand corner here, we want to add a 5 volt connection. So in this case here, I've just gone W again. Sorry, I'm going to keep on forgetting to say what I do. Type in 5 volts there, and we'll drop that in. Now that part of the circuit is done. Quite tight on the room, so I'm just going to move that over. Then we need to take the rest of these parts over here. So we do the same thing, A to add a part, R to grab a resistor, bring that down, put it there, W to draw a wire, and we're still in the wire mode, so we don't have to hit W again. And then in this case here, I've already got a 5 volt on the board, so I'm just going to hover over that, press C, and now we have a copy of the 5 volt marker, and we'll just drag that in there. And then, because I'm lazy, I'm going to copy and paste that using Control C, Control V. So there we go. Now add some values to these, 10K, hit V again, 10K. Hopefully you're getting the idea of what's going on here. In the interest of time, I'm just going to delete that and copy, actually I'm just going to delete that there, and copy over from here, because I have a little bit more to go through, and then just need to connect C, so we'll go W, draw a wire. One thing you might notice here, which is a bit different, you've got all these crossings here with green dots on them. They're a junction, and so that means that the wire at that junction there are connected. You'll notice down here, there's no junction, and that means, sorry, those wires are jumping over each other with no connection. And so if you're wondering what's going on there, and then we'll just grab a ground and we'll bring it there. So we've got our two encoders. The next step that we need to do now is associate a footprint to them. So a lot of CAD packages, when you bring a resistor in, you will bring a resistor in and it will be the exact physical resistor dimensions, whereas in KiCad they split kind of the schematic representation and the layout representation in half. So we put down the abstract symbols here, and then we do a linking step between the two. And I've just realised I forgot to change the labels. So go in there, E is for edit, and we'll change that to 2. Change that to 2, and then copy that over there. And change that to 2, and then you might notice that there's no junction at that point that we just created, so we can grab a junction off the side and drop it down there. So now that's all good to go. The next step is we need to annotate these parts and give them a unique identifier, and so we can go up here to annotate, just goes through and adds unique IDs to them all. And now comes the footprint association step. So hopefully this will load quickly. If I've loaded it before, it will be quick, otherwise it might take it's happening. Basically what we'll have in the center here, come on, there we go. So this here gives us all of those unique identifiers that the board is labeled with down there on the left. We then have the kind of number, so you can see the 10K resistors will be down here. So you can see that's the 10K resistor that we added with 10K next to it. This is why you need to put values on there so you know what they are. Now what we need to do, this is kind of the symbol representation, we need to give it a physical footprint. And in this case here, we want to make it an 0603, which is just a size. I'll pass around a ruler, which is from DigiKey. It's got a bunch of different footprints and sizes. It might be a bit hard to find, but to give you an idea, the parts are quite small, is a long story short. These 0603s are large enough I can do them without a microscope, but if you haven't done a bunch of surface mount before, you may want to go a little bit larger. So in this case, here, just go down on the left and try to find the resistors. So resistors SMD's surface mount device. We'll go over here on the right and we'll find 0603, which is that one there. We'll just double click to assign it. And so now we have the association made in the middle. We'll also go down to our encoder here. And now KiCad does have a footprint for a rotary encoder. However, a lot of their designs don't have 3D models with them. And I really like adding 3D models to my designs because that way you can see what it's going to look like before you actually get the board manufactured. So in this case, I've made my own library called Keyboard, which has a few bits and pieces in it up there in the top right-hand corner. A lot of these, I just took the KiCad library, added a 3D model to them. Other ones I built from scratch, such as the micro USB. I picked up a crazy deal. It's like 2 cents each for micro USB connectors. So I bought 100 of them off, from AliExpress, and now I just have them in my library to put in there. In this case, we'll just select the rotary encoder. That should be everything. And then we can go OK. And that's all good to go. So we can now go into the layout step. One thing that I'll show you whilst we're in here that you normally do at the end is you can export a bill of materials. So this here gives you a big CSV with all of your part numbers, which means you can go out and buy them quite easily. And if you associate part numbers in this setup here, you just get a big list, you give it to DigiKey, your parts magically show up 4 days later. So with that said, I think, go back to the slides now. Yeah, wonderful. So PCB layout, compared to the schematic, is the physical representation of the circuit. As you can see, if I had to draw that up and try to figure out where all the pins are on a tiny board that there's 50 millimeters long by 22 millimeters high, it would be quite challenging to see where everything is. But that's why we do it on the schematic, and we can make it look nice before. The other big important thing with this is that you want to make sure all of your physical locations of parts are in the right spots. So things like you don't want to have a USB connector in the center of the board. It's going to be hard to plug your your cable into. It's also got mechanical requirements for mounting holes and stuff like that. Interestingly, the first step before you go out and lay your board out is you need to make sure you know where it's getting manufactured at. So all the different manufacturers have different requirements for boards, different minimum dimensions that they can make. And this is important because if you design a board that's, say, following a really, really advanced process and you go and try to get it built for cheap in China, they're just not going to be able to build it for you, or they'll send it back and it won't work. On the other hand, as I'll show in a few slides from now, you can make tiny, tiny changes. So 0.05 of a millimeter changing the size of your drill bit might quadruple the cost of your board. And I'll give you some demos of that in a second. But you've got a bunch of different things which I'll go through that can change it. For those who haven't done much work with PCBs before, I'll quickly go through the layers on a board. So at the top here, it's a bit hard to see, but you've got this white, what's known as silk screen. And so this is typically what you see on the top of the board. It's got like connectors here, part numbers and all that jazz. You then have your solder mask, which is typically green. In this case, it's orange. And that is a non-conductive kind of insulating layer between the copper on your circuit board and the rest of the world. From there, if you were doing a 2-layer board, which is what most boards are, and that one that's making its way around the room is, you'll only have a layer of copper right at the top there and a layer of copper right down the bottom. In this case here, this cross-section is a 6-layer board. I picked it because it looks really nice. And so you can see that there are extra internal layers, but that's not normally the case on a lower end board. You then see this fiberglass in the middle here. It's typically what's known as FR4, which is a flame retardant spec. It just kind of identifies what materials in the middle. You can get more exotic ones, but they start going up in price. And that's basically then mirrored again on the bottom. One thing you'll notice is this big hole that runs from the top to the bottom of the board. This is called a via, and what this allows you to do is if you have a trace which is on the top of the board, you can take it down to the bottom of the board or even a middle layer. So as you can see on this one here, it looks like it's connected to whether it be layer 5 there, and then it might not even be connected on layer 6 because there's no copper around it. So depending on what your board is, you'll have vias. Most of the time they run the whole way through, sometimes they'll only run part of the way through. Design rules, this is where you need to check with your manufacturer first. So this is an image from Lintech, who actually make really nice high-end boards out in Queanbeyan. Basically, the three main dimensions you need to keep an eye out for are what is known as the minimum trace and space. So the minimum thickness, so say down here with C, of how narrow your track is. And then up here with D is how close they can be together. Basically, the way that they etch them is they etch down as a trapezoid. And so if you've got two tracks that are really close together, when they start to etch down, they're not going to etch far enough, and you'll have shorts between your traces. The other important things is the drill size. It's not shown on this image, but imagine just how small that black circle is. Obviously, smaller drill bits, some of them are so small you can't get, and also the smaller you get, the more often they break, so the more they cost. And then there's also what's known as the minimum annular ring, which is this gap around the via. You may also see it as minimum via size and minimum drill size, where the minimum via size is the drill size plus 2 times the annular ring. And the reason why that's there is because this is a surprisingly manual process. It's literally people picking up things, stacking them, putting them in ovens and things like that. And so they don't have perfect alignment between every single stage. So you might only have, say, 0.1 of a millimetre of an annular ring around your via. And so if they're off by 0.1 of a millimetre in the positioning of their drill bit, your circuit board may not work. So with that said, let's have a quick look at the cost factors of it. So this here is PCB Wave. They're one of the many manufacturers of boards. I don't normally get mine built here because they're very cheaper people, but they do a really good job of showing price. So in this case here, I've got a basic 2-layer board. It's 100 millimeters by 100 millimeters, and it's a whole $5 for 5. It's ridiculously cheap. One thing we can do here, if we up the dimensions of it to 101 millimeters, and we update this, you'll notice the price goes flying through the roof. So one thing we'll see in a second, that keyboard, its maximum dimension is exactly 100 millimeters, because if I went to 101, I was going to have to pay 5 times as much for it. You'll also notice as you go down here, you can change the minimum trace sizing, so you can see the price starts going up as we use smaller tracks. You'll also notice that, okay, we've already got that set. If we go back to 6.6, and then, so we go from a 0.3 to a 0.25, the price jumps up there. And we can keep on going down. They actually don't charge more for different solder mask colours, which is awesome. So you can have whatever colour board you want. And there's a few other settings here playing around. Instead of having a silver finish like those boards do, you can have a gold finish. You'll see that knocks the price up. If you go all the way up to hard gold, it's going to fly through the roof. But these are just things to check before you go laying your board out. Because obviously I'm picking extreme examples here, but there are some things where you might be indifferent between 2 hole sizes, and it could save you $30 or $40. Oh, no. So I have been asked to record it by a few people, which is why I've got that up there. So PCB Layup, once again, this is if you're kind of going through it later. I'll go through it now. So from the schematic tool, we can hit this Run PCB New, which is a layout tool in KiCad. Take a second. Wonderful. So you can see here, I've got most of the keyboard laid out, but there's a few bits missing up in the top there. Quickly going through this for folks that haven't seen a layout tool before, we basically have top copper, which is these red traces here, so that's any copper which is on the top of the board. We have green, which is on the bottom. Different CAD packages have different colours, but it's just identifying different layers. If you've got 4 layers, there'll be 4 different colours to pick from. We then have over here all of these yellow circles there, all the drill hits through the board. So this has mechanical keys going into it, so you need something physically to hold them down. You will also see a yellow line on the edge, and that routes the board out and gives you your defined outside size. So with that said, what we're going to do is we're going to press the Update PCB button up here, hit Update, and it will bring all of our parts in that we had just done in the previous step. From there, we can just select a part, hit M to move it, and I want to hit R to rotate it, so I'm going to place that about there, looks good. We can pick up, and blue here is the solder, the silk screen, which is that white stuff on the top of the board. In this case, blue is top and purple is bottom. We'll move that there. What we'll then do is we can grab all of these parts, hit F to flip them upside down. So in this case here, all the parts are on the bottom of the board because we've got the key switches on the top, and so there's not enough room to put parts there. And now what we can do is we can just pick parts up, move them around, and you'll see that there's this white line that jumps all over the screen. That's called a rat's nest. I don't know how it got its name, but it's basically telling you that in this case here we can see pin 2 wants to be connected to pad B over there. And so what we do is we move these parts around and we orient them until these rat's nests are kind of minimised in length. So that means we don't have to run tracks snaking all around the board. So we'll pick up another one, and we'll move this down here. Where does that want to go? It wants to go over to the left, so we can put that there. Let's do one more. Ooh, can we grab you? And it's over here on the left as well. So there we go. Put our parts there. Now, let's just pretend all the parts are in the position. You normally go through and place all of your components before you start routing. It just makes life a little bit easier, because the main reason is because you can move the parts around without tracks associated to them, get them in their perfect positions, and then run tracks. So in this case here, what we want to do is we want to press X to draw a trace. And so in this case here, the CAD tools are smart. It will only let you connect it to the pads you're allowed to connect it to. So in this case here, we want to connect it to both that pad up there and pad A. In this case here, we have this pad. You can see the yellow is pushing us over to the right, and we'll run it over here, and we'll see it wants to connect to this red trace. But as I mentioned earlier, these are on different sides of the board. So to connect them through, we need to run a via. And so in this case here, what we can do is we can press a V, which will drop a V down, and then we can connect it up like that. That's not a very good job, so I'll just bring it back so it looks a little bit nicer. And so now those tracks are connected, and there's no longer a wire. There is a rat's nest running to another component on the board, but not between those ones there. This is where you go through and add all your traces. In the interest of time, I'm going to do the board outline now. So you can see here, we've got the board outline that runs up on the right-hand side and then just magically stops. And so in this case here, we're going to select the edge cuts layer, which is where they route the board out, cutting around the edge. And then we'll pick this kind of radius tool, we'll go in here, select roughly the center. Okay, I've already got one on here. That wasn't meant to happen. Let's just pretend that there was never a corner around there. So now we can grab it in the center, run out to that point there, draw our radius around, and then we'll grab the straight line tool, select there, go all the way across here, and now that's connected. And so we can press Alt-3 to go into the 3D viewer mode. And now what we should hopefully see, we'll have some parts floating up in outer space at the top once it loads. But you can see we've got the board outlined with all of our rounded corners. And if we go around to the back here, you can see the parts that we've just placed and the trace that we have running between them. One final thing that I'll show here is that you might notice there's still a lot of other rat's nests across the board. If we zoom in, you'll notice most of them are ground and power, and that's because instead of running an individual track to every single ground pin on the board, what you'll normally do is just flood fill the whole remaining side of the board. So in this case here, what we'll do is we'll grab this add filled zones tool, and then what we'll do, go up into the corner here, select a spot, and I'm going to click up on copper there. Now if we try it, it should allow us to select copper. There we go. So in this case here, we want to go on the front, and we want it to be ground, and we'll press OK. And then what we'll do, we'll just go in and kind of enclose the whole board. You can go over, no worries at all. And let's go back up to the top. And so now you can see we have a bunch of copper fill on the board. That line you see running around there now is the 5-volt rail. So if we want to put 5 volts on the bottom side of the board, what we can do is we can click up here, Control D for duplicate. No, I've duplicated the wrong thing. Control D for duplicate, paste it back down, and then we'll go in here and we'll change it to 5 volts. Press OK. It will fill the other side, and now a lot of those nets are gone. The ones that are existing are just because I haven't put the components in, but you get the idea. Now, before you send the files off, you want to make sure that all your tracks are connected where they should be and they're not connected where they shouldn't be. This is where a tool called Design Rules Check, up there, that little bug, you can click on that and we'll press run. And this is going to throw some errors because we don't have everything connected. Annoyingly, KiCad hides them on a second tab, and I have fallen into troubles with this multiple times. So I wish they would add that onto one of them. I know a lot of other people share this concern, but basically we'll go through here and it will tell you that all these parts are unconnected, which is what we want. And basically want to make sure that DRC is completely free of errors before you continue. One thing I forgot to mention is that you do have a very similar thing over here in the schematic tool called ERC, which is Electrical Rules Check. This is checking that all the pins are connected properly. DRC checks you don't have pads too close or too far away from each other. So hopefully if we run this, D is not connected. Okay, so I can put a non-connect. Right. Okay, I've moved something, that non-connect pin's moved, but we will pick that up. This is just telling you that, anyway, if you could place it there, it would get rid of that error and everything would be good to go. So, with that said, when you have, actually, no, one more thing, sorry, I forgot. There's a really cool extension. This isn't part of KiCad, but you can add it in really easily. It's called Interactive HTML BOM. When it comes to placing all these parts on the board, it can be a real pain. You've got to go through, see the number that you've got marked on the board, then you go in and dig through your bag of parts and find the right one. Here we go. What this does here, it takes all your KiCad files and basically gets you ready to be a human pick and place machine. So what you can do here is you just select the top bit here, and now it will show you every single 100 nanofarad cap on the board. It will show you where pin 1 is, and this means I can get 7 of those caps out and place them all down in one go. I then press N to go on to the next one. I've got my 22 picofarad caps for the crystal, and you can keep on going down like that. Let's find a big part. Actually, there we go. So the LEDs, for example, they're directional. They have to go in a certain orientation, and it will mark pin 1 for you. So this way you can make sure they're the right way around. It just makes assembly a whole heap easier. And there, that's a pretty cool tool. When it comes to ordering them, you export your Gerbers, which I will quickly show. Oh, we're back on this screen. Okay. You can tell I'm not normally out the front. Here we go. What are we doing, computer? Here we go. There. You export, you go up here to the plot, you select Gerber. Gerber is basically the PDF of getting boards manufactured. Everyone accepts it and explains where everything's meant to be on the board. You export that. You then check it because there are things that will look fine on this screen here, but when they export to your Gerbers, like minimum distances between things, the Gerber will do post-processing on that and stop it. I've fallen into problems with that before, so just make sure you check your Gerbers. KiCad does have a tool inbuilt to do that for you. From there, put them into a zip folder, upload them to the manufacturer, just the same site we were on previously. Select all your options or the board. Don't forget to order your parts. I've once again done that before. The boards show up. I've got no parts to put on there. Then once the boards begin, you get to assemble them. So for surface mount assembly, you can do it by hand with an iron and some solder. In this case here, I'm going to show you very quickly what reflow soldering is. So we basically put a board in between a bunch of other boards. We then get a stainless steel stencil. It's normally about 120 microns thick, and it's got a bunch of holes cut out, which is where we want all the solder paste to go through onto our board. So we carefully position that on top of the board. We then get our solder paste. You can use a credit card. I just picked up a kind of metal thing from Bunnings for about $3. It works great. You then go and slide that over the board, and what you get is all of the solder paste exactly where you want it to be, and none of it where you don't want it to be. Or in the next one, I'll show you it into a very good job. This is a close-up because I managed to get the camera in focus. You then go through and place all the parts. As you can see, I've done a pretty horrendous job of placing the parts here. They're all over the place. If you look closely, this one here is the wrong way around. All of the green lines should be at the same side. But fortunately, because the solder's not solid, you can go through, correct them all, get them in slightly nicer alignment. Or in this case here, I managed to get them spot on. The first one I was trying to use a vacuum tool and it wasn't working too well. And then there's the whole board. I know this isn't a keyboard that I've been talking about. I've assembled all the keyboards, so this was the closest thing that I had. Then put them in the reflow oven. This is just like your normal oven, except it follows a very specific temperature profile, which is crucial to getting all the solder melting properly. I put it in there on top of some boards just to keep its thermal mass down and get it reflowing better. When they come out, it looks something like that. You may notice that all the LEDs are slightly skewed. I have the wrong footprint on the board, but they're all connected. It's all good. This is one case where they're not connected. It might be a bit hard to see on the screen, but the second pin on that resistor pack there doesn't have any solder on it. And so this is where you'll manually go through, find issues like that and rework them. And you'll get a board that looks like this, which everything electrically works fine. But you can see there's this flux on the board, which is a liquid that helps all the solder melt and things not stick where it shouldn't and things stick where it should. And so at this stage, I'll run it through an ultrasonic cleaner, wash it underneath the tap, and then put it back in the oven for 50 minutes at about 50 degrees Celsius to let it dry, and then you're ready to go again. And the end result is you get your board, you check it, and it all works perfectly. In this case, I'd go through with the keyboard and manually check all of the pins were connected using a set of tweezers before I soldered the keys in. That way I could rework any issues that I ran into. Mechanical design, I'll quickly fly through this. Obviously, circuit boards are cool, but sometimes having them in a case is required. You can laser cut things, 3D print them, buy off-the-shelf enclosures. You can even use PCBs as faceplates. So, in Fusion 360, which I know it's not an open source tool, but it's the best free CAD package. I've got an education license. You can also get hobbyist licenses if you're not making money off using this, which is great. So in this case here, I exported the keyboard from KiCad. There's a setting in PCB new. I brought into Fusion 360 and I've designed my case around it. The nice thing with this is that instead of me having to get a ruler out and measuring all the physical dimensions, you can use a kind of option within it called project, where you will click on a part on the circuit board, it will project it out to your screen. So for example, this tiny little hole here, I know I've made it oversized, but I picked the center of that switch on the board and I brought it out, so I know everything's in alignment. If you don't have a laser cutter, which I don't, unfortunately got access to one here at ANU, you could 3D print things. So this here is the programming jig that we used to flash all the badges for B-sides this year. In this case, I wasn't able to export a step file from KiCad because the tools were new and playing up. So I just took a photo of the badge, brought it into Fusion 360, scaled it to size, and then just manually cut it out. And so in this case here, that's that board. Then using Project, we managed to design a kind of enclosure that would fit around it. We've got the programming jigs in there. This was a rush job. I think we did it in 48 hours and we had 5 of them and it did a great job. So the other option is if you want to get off-the-shelf components. In this case here, I designed a board around this aluminium extrusion that I picked up off AliExpress. So not only did this is here to check the board fits properly, they don't have any mechanical clearance issues, I was also able to design the front and rear plates, once again using Project. So in this case here, I made a mechanical drawing in Fusion 360, exported that as a DXF into KiCad, then drew all the extra features on in KiCad, and then in this case I brought it back in just to check. And so this is how you can get really cheap and custom end plates made, and so it cost me $5 per side, which was pretty cool. And then on the keyboard, so I did the exact same thing. So the top plate on the keyboard is actually a 1.2mm thick PCB. I couldn't get any acrylic that was narrow enough to fit into the key switches, and so I just went out, got a board fabbed. In this case here, I drew it all up mechanically in Fusion, brought it back into KiCad, and it was all good to go. So firmware, you need to get your code on there somehow. For the keyboard, I only had to flash it once, and so what I'm using is these surface mount pads on the left here with a $5 programmer off eBay and some pogo pins that I built. You just press it down, hold it for 30 seconds, it gets the code on there. If you are doing longer development, so that one in the case that I showed, that's been on my bench for 4 months, just struggling getting it to work. And so in the top left-hand corner, you can see a permanent connector that will sit there. The nice thing about this compared to doing over USB as well is that depending on which micro you use, you can also have full debug capabilities on this. So unlike with an Arduino, you just print everything all the time. This here runs an ARM Cortex core, and so you can get in, you've got all of your single stepping, breakpoints, looking at memory stack. I don't really know what most of it does, but you can go in and do it all. Keyboard firmware, for those interested in the keyboard, when you buy the micro from Atmel, it normally comes with a bootloader. I bought mine off AliExpress for cheap, so I had to put a bootloader on there. So I just pulled the Katarina one out of Arduino. That was nice and easily. There's a really cool open source keyboard firmware called QMK. I'm sure a few people here, if you've got mechanical keyboards, have used it before. I learned about it during this process. It's awesome. It does all of the low-level stuff for me. The way that it works is it sends HID codes over USB to the computer, where the computer then uses auto hotkey to process them. And so it means that if I'm in Fusion 360, it will send some set of key codes. If I'm in KiCad, it will send another one. If I'm in Chrome, it sends another one. You could also hard code those HID codes onto the keyboard if you don't have access to auto hotkey because you're not on Windows or something like that. So final product, on the left there, I've now got a really cool custom keyboard, which I originally designed for CAD, but the biggest thing I have now is my music controls hooked up to the 2 encoders, and it works great. You just twist it one way or another. During the build, I learnt of QMK. I was originally just going to roll my own firmware, but QMK is awesome. So the keyboard on the right was purchased after the building of the keyboard on the left. And the thing I really like about it is because it's completely reprogrammable, I've got the keys doing a bunch of weird stuff. I've had issues and still kind of do with RSI, and so I've been able to change configurations on my main keyboard that have helped mitigate them so I don't have to move my hands as much. And all, at the end of the day, it just looks really cool on my desk, except the rest of my desk is a mess. And so that's why it's a tightly propped shot. I know I'm running over time, but when it comes to making profit, if anyone's at B-sides, you may have seen the Hacker Chicks add-on down the bottom there, which Kylie and Echo, who built the main badge, had. You may have also seen me in the Hardware Hacking Village with the War Games one, which is the blue on the top right. Or if you're at DEF CON or browse the internet last year, there were a bunch that were at DEF CON. These boards are a great way to get into it. They're primarily an artistic side of things. As you can see, mine looks the worst of all of them because I have no art skills. But yeah, I gave away 10 assembled boards. I then gave away 10 boards with all the parts, and I was giving out bare boards at the end because people are going to go home and build them. And so you could quite easily fund your trip to B-sides. by selling add-ons, and not to mention have a chat with a bunch of great people, trade them. It was good fun. If you're interested, there is a reference design on the GitHub repo for this that has all of this schematic done and all the parts in the layout tool. So if you don't want to worry about all this electronic stuff, you can just go in there and make a really cool board. If you do want to, and I'd strongly suggest going from the start and working through, but this is a good reference design. And then finally, if you want to learn more, take a photo of that top link there. There's a CSides folder that has everything that I've gone through today. The README also contains a bunch of information for PCB design, guidelines, how to do PCB art, you name it, you can probably find it in there. If for some reason you still have more questions or you just want to have a chat, please get in touch. My contact details are down the bottom there. I like to think I'm somewhat helpful. And then I also have a massive box full of circuit boards that I've brought along that I've built. So at the end of tonight, if anyone wants to come and say good day, ask me questions, I've got everything from blinking LEDs through to vector network analyzers. So any questions? No? Okay.
Yeah. So populating the boards.
Yes.
Are we basically still using the vacuum kind of tools?
So I tried that on the first one and it kind of sucked. So I just use a small set of tweezers and do it. So if my parts were bigger or the LEDs had a flat top, I think I would have had more luck with the vacuum tool, but they had a really tiny touch point, and as soon as they rolled over, they were gone.
Obviously there are low run kind of PCB manufacturers out there now, but are there any low run TNT that will...
Yeah, so you've got PCB Way and other companies like that. They will do assembly, so they'll do fab and assembly for you. Right. Cheap is an interesting definition, but the Chinese fab houses do a pretty good job, and they do a reasonably cheap price. Normally 500 is a break-even point, but it really depends on a bunch of factors on the board and how many parts you've got, how many different unique parts and all that jazz. So, yeah.
How many boards roughly can you get of roughly the same size as your reflow oven?
2. So I can get 2 of those keyboards in there. The biggest problem with that reflow oven is that it's only hot in the middle. It's not hot on the outsides, and so I run as few boards as I can through there. At most, I kind of use a 100mm by 100mm area in the middle. So some of those keyboards, the resistors in the top right-hand corner, not the top left for some reason, just the top right, weren't reflowing. So, but it also depends on the reflow profile. If you run a slightly more aggressive profile, you might be able to get away with more boards in there. So. Yeah.
Where did you get that reflow?
Bought it off eBay. So it's the T962 from memory. It's about $250. Let's go back, T962, about $250 off eBay. Out of the box, it has masking tape, which smells as soon as you turn it on. It also has a really bad temperature control and has really bad firmware. All those 3 fixes cost about $10 in a morning to do. And then the oven isn't great, but it does a good job for its price. So.
I've never used Eagle before, but how does KiCad compare to Eagle?
It's going to start a war if I make a comment on that. Back in the day, Eagle was much better than KiCad. I'll argue that KiCad's getting there. If it's not the same, it might be slightly worse. The fact that it's open source and people can write their own pick and place plugins for it, I don't believe you can do that with Eagle. The other thing is Eagle has quite strict restrictions on the board size. So if you go bigger than a physical dimension or a certain number of layers, you've got to start throwing them money. They do educational licenses, which is good if you're a uni student. They don't do hobbyist licenses like they do for Fusion 360, and professional ones start costing in the thousands. So.
How much is an educational license for Fusion 360 cost?
So education's free, professional ones I think are $500 US a year. It's very reasonably priced, and if you're earning under $100,000 or something, it's discounted. Or anyway, their website's got all the details. So.
2 questions. Parts libraries, can you talk about that, and also auto routing in KiCad, is it worthwhile? Okay,
I'll go to auto routing. I never use it because I hate auto routers. I don't believe it's very good. That could be why, but I do everything by hand. I have very strong opinions on that. Parts libraries are pretty darn good. They have a lot of parts in there with the unique codes for them. So I needed a DC barrel jack. I didn't want to worry about making my own. I just found the code, went to DigiKey, ordered it straight up. I would say that 95, so if I wasn't particular about my symbols, 95+% are in the KiCad libraries. I'm quite particular about them, so I will go and take their thing, change it. But they're pretty good, and then it's the same thing because they're not the schematic symbol and the footprint aren't hard linked. You can have a lot more options in there because you can have a resistor, and then you've got 30,000 multiple hundreds of different resistor footprints you can have on your board. So.
And I've never used Fusion 360 before, but is there a parts library for all the parts to go?
Okay, so it hooks up to McMaster Car, which is a big US distributor of parts, and so all the screws in here were imported directly off the McMaster Car catalogue. Otherwise, I just jump on the internet and type in a part and then step after it. So a step file is basically the PDFs of the 3D modelling world, and so if you can find a step file, you can bring it into Fusion 360. It is a bit weird, you've got to upload it to their website first, but you can get it in here at the end. So, thanks.
Do you have any tips for cost-effective front panel manufacturing options?
I haven't done much of that. I have done one whole board with front and back panels, which was just PCBs that I built. Made them look nice, cost me $5 each. Going to aluminium milling, I haven't done that before. So, but if you want to have a chat about the boards, come up to me later and talk you through it. So, cool. Oh, thanks everyone.